Okay, what we had here when I originally drew it was a series of wavefronts approaching a wall with 1, 2, 3, 4 openings in the wall. You can kind of see the opening for 1, you can see the opening for 4, you can see the waves dispersing from each of the 4 openings, but you can't really see the opening at 2 and 3 because of things that I've superimposed on it. We want to understand the angles at which this configuration could give us interference maxima and interference minima. First, let's think of the simpler 2-slit situation that we saw in our preceding class. We have waves coming off at angles theta, practically equal angles because the wave is going to be observed at a great distance, much greater than the separation of the slits. So these angles are essentially equal. These paths are very nearly parallel, although they will eventually converge. You recall we could construct a triangle here that has angle theta here, similar to this angle theta, and the path difference between this path to the detector and this path to the detector is just this leg of this triangle. Okay, and of course you have a right angle here, and this side goes along the wall, and this side goes where it has to go. Okay, now as the wave fronts come in here, the medium or the 2 slits, we drive the wave with a frequency equal to the frequency of the wave, the incoming wave, so that the wave that goes out here goes through its cycles, similar to what we have here, okay, and this one goes through its cycles, similar to what happens here. But they don't go through the cycles at the same time. If this path difference is half a wavelength, or alternatively, if it's n plus a half wavelength, whole number plus a half a wavelength, then the rays are 180 degrees out of phase, okay, because this corresponds to half a wavelength, so that this wave starts first. This wave doesn't get here until it's gone through half a cycle. So it's got to be 180 degrees out of phase. Half a cycle being 180 degrees of phase, as you can understand up here. From this point on, this path has the same length as this path from here to here. The only difference is the path difference here, and if that path difference is half a wavelength, then this one is half a wavelength out of phase with this one, which is 180 degrees out of phase. So that when you draw the phase diagram, if this one is at this phase, okay, and that would be like this on the unit circle, then this one is at this phase here, represented by the orange arrow, which would be 180 degrees out of phase. Now, we draw the arrows this way and this way. Okay, we draw them horizontal in this case. Put one of them at 0 phase, the other's going to have to be at 180 phase. But of course, these phases go through all angles as they go around the circle, but they're always equal and opposite. I didn't quite get the direction of that opposite this one, but it should have been. So as they go around the circle, as this goes around the circle this way or this way, it doesn't matter. This one is always 180 degrees different than this. And we represent that 180 degree difference by an arrow in this direction at phase 0 and an arrow at this direction by whatever this is out of phase. Okay? So, that's this picture. And if there's more than a whole number of wavelengths, this also applies, as long as this one is a whole number plus half a wavelength out of phase. You're still going to have the 180 degree phase relationship. Okay, now we want to come over to this picture. And I'm going to pause a minute just to get my bearings. Okay, now let's assume that the path difference between what goes on at the first slit and what goes on at the third slit is half a wavelength. Now, I've drawn that. I've drawn the green triangle here between the first and the third slit to indicate that the path difference between the wave that comes out here and the wave that comes out here is half a wavelength. Now that's also, of course, going to be the case between the second and the fourth slit. Okay, the second and the fourth opening are equally spaced, but have the same spacing as the first and third. They won't be in the same phase as the first or the third. Second, fourth will be in a different phase in most cases, but they'll still have the property that if they're half a wavelength out of phase, that's going to cancel the wave. And if this is light coming in here, what you're going to see if you shine the light, if you put a screen out there at some great distance, the light's going to cancel out at this angle. Okay, and you're not going to see any brightness on the screen at the point that corresponds to that path. Okay, well, we'll see that. We see that in lab. So I'm going to say the path difference from 1 to 3, between 1 and 3, is half a wavelength. Then the question I posed, and you should think about this without looking at the answer if you haven't already seen it, or even if you have already seen it, see if you can remember what you understood at the time we did it. Question then is, how far out of phase are 1 and 2? Okay, if 1 and 3 are 180 degrees out of phase, how far out of phase are 1 and 2? And the answer is, well, you should have paused and thought about it. We draw the triangle between 1 and 2. We see that we have half the path difference. Okay, well, the wavelength is still the same, so if the path difference here is half a wavelength, the path difference here is a quarter of a wavelength. And I'm wondering if I got the first part of this. Okay, I'm being distracted by something going on over here. We'll worry about that after I paused the video and recorded it. Okay, anyhow, this path difference is half of this, so this is a quarter of a wavelength. So the path difference between 1 and 2 is a quarter of a wavelength. That puts it 90 degrees not out of. I didn't have room to write out of, but I wrote out of phase. Have to be grammatical. Okay. Now, you might think of how we would draw these arrows if the path difference was a quarter of a wavelength, okay? If you were 90 degrees out of phase. And we're going to do that in a minute, but you want to think about that. It's also possible you would get destructive interference if this path difference, instead of 1/2 wavelength, was 1 plus 1/2 or 3/2 of a wavelength. Okay? So what would the difference be between 1 and 2 that would give you 3/2 of a wavelength here? Well, 3/2 of a wavelength, well, this would be half of that. Instead of 3/2 of a wavelength, it would be 3/4 of a wavelength. Or you could say that 3/2 of a wavelength corresponds to 360 degrees. 3/2 of that's 540. The path difference between 1 and 2 is half the path difference between 1 and 3. So that one way or another, you would say, well, if this is 540 and this is half of this, then this has got to be 270 degree path difference. Alternatively, you could say, well, if this is 3/2 lambda, then this has got to be 3/4 lambda. So you're going to have 3/4 of a wavelength, 3/4 of 360 degrees, or 270 degrees. So you can have 270 degree difference between here and here, and that would still give you destruction between here and here, or between here and here, destructive interference between 1 and 3, or between 2 and 3, and you would again get a destructive interference at your detector, the screen or whatever it is you happen to be detecting the wave with. Now we're going to go a little further with this, but hopefully you understand what we're talking about so far.